Welcome, and we're going to talk about another concept related to trigonometry. It's actually taken from physics. It's called harmonic motion, and we're going to focus first on simple harmonic motion, and then we'll talk about damped harmonic motion. But the idea with the first one, simple harmonic motion, is that I want you to think about a spring with a mass on the end. And I have a diagram down below that you might find useful. But the idea is that you take the mass, and when it's just resting, it's at what we call equilibrium position. And I should also mention that we consider all this in ideal conditions. So there's no human error, there's no friction, there's nothing to really stop this motion once we get it started. But you take the mass, and from that equilibrium position, you either push it or pull it vertically. I'm assuming it's vertical. It can be left and right. It doesn't much matter. But then after you pull or push it, then you release it. Okay? And so I just want you to take a minute and think, what is going to happen as you look at the displacement, which is position from the equilibrium position over time. So how does that displacement look? And so here I have kind of an idea of what the motion would look like. Maybe you want to take some more time and think about it. Also, I understand that video now rules our life, and so if you want to view this as an animation, I've linked a few GIFs. Here is the first one, so you can see the mass is hung vertically, and the spring is vertical, and the mass is at the end in blue, and then it makes this red sort of motion. And then here's another one. This time the mass is red on the end of a spring, and then it's tracking how far it extends from that equilibrium position, which is this horizontal line, over time. Okay, and I hope that you start to maybe see something interesting with these animations. Now, before we go and discuss the mathematics, I feel obligated to tell you a little bit about the physics. And the idea here is that when you pull the object from its equilibrium position, naturally, if one of Newton's laws is if it's for every action there's an equal opposite reaction, so when you pull it, it naturally wants to spring back to its equilibrium position, and that force that is exerted to try to move that mass back to its equilibrium position is called the restorative force. And the only problem with that is, yes, it will try to restore it to its equilibrium position, but with the absence of friction and air resistance and all that stuff, it's going to push it past the equilibrium position. And then now it's too far the other way, and then it pushes it back, and it just continues to try to push it back to that equilibrium position, but it overshoots all the time because it's in ideal conditions. Okay, so now, physics aside, you will learn much more about the physics, I promise, if and when you take physics, which I hope you do. But where's the math? Well, if you happen to look at this carefully, right, and you saw it pop up on the screen when we were looking at those GIFs, at least, if you were to connect the ends of, or the mass position, and look and track that over time, it actually makes a wave. It makes a sine and cosine wave. Oh, so this is why we needed to know the graphs of that stuff. Yep. So the mathematical model, when we look at an object experiencing simple harmonic motion, or rather it's oscillating in ideal conditions, then its displacement, again, that's the distance, or the distance from that equilibrium position over time, is given by, and you notice there's a sine function or cosine function in there. D is equal to, so displacement is equal to A times, and this is omega. It looks like my physics teacher in high school called it a butt, like B-U-T-T, but it's called omega. It's the Greek letter omega. Okay. And so it's either a times sine of omega t or a times cosine omega t. And then we have simple harmonic motion. We also might remember that being that this looks like a transformation of the sine and cosine function, which it very much is, we have those concepts from section 4.5 pop up again: amplitude, period, phase shift. Okay, amplitude here is just going to be the opposite value of A. Again, A could be negative depending on where we start. Period of motion, we remember that that's 2 pi over b, so in this case it's 2 pi over omega, and I need to write omega properly. Okay, and again, that's just the time for it to make one complete, at least in terms of the spring, it would be down and up or left and right, depending if it's horizontal or vertical, but one complete repetition of the motion. Okay, now the only thing that's really new to us is this idea of frequency, and that's most often, at least if you think about springs, you can talk about it in terms of frequency, and later on when you get into physics you'll be working with tuning forks. Those oscillate or vibrate at a certain frequency, and that's just simply 1 over the period. Okay, and I believe they actually use lowercase f for this. Okay, phase shift, since there really isn't a phase shift, most of these models should have a phase shift of 0. If it isn't 0, then it's kind of odd, because when you stretch it out or compress it, that's usually the maximum or minimum that you're stretching it to. Okay, units. Alright, amplitude is going to be in the same units as displacement, so I'm just going to write displacement units. Period should be a time. Now frequency, this is 1 over time units, which we actually, assuming that time is in seconds, then this is going to be a unit called hertz, like it hurts really bad, or actually like Hertz car rental. Hertz. And then phase shift doesn't have any. Okay. The last thing I want you to think about is which model should you use? We noticed that we had sine and we had cosine. Well, think about the behavior of the graphs, right? So if initially you have the spring at the equilibrium position, that's when you're going to use sine. If you initially have it at maximum or minimum, that's when you're going to use cosine. So just keep in mind, so just notes here: sine, start at 0, cosine, start at max or min. Right? And so this is just the overview of simple harmonic motion, and then next we'll get some practice with examples and look for that oscillating type behavior.